Okay, so
Did I enter my Capcom?
let's chit chat.
Get away from my desk. I'm
not.
Okay.
Give
me my paper.
Why are you mad at me?
What were your?
So
Not fart.
okay, so let's start with that first question. So you have two wires, and they were actually nice to make sure that you understood, because not only did they put the X there that indicates the current's going into the current, or into the page, they even drew an arrow that said, hey, if you don't know what the X means, this is what you got. And then they got a dot here,
No, that's like an 18 test.
and the current going this way.
No, they like it.
He wrote these, but not the ones
Now,
that have the different.
here's the thought process that you want to, you need to be able to go through. And obviously, if you can figure out one side, you can figure out the other side. So, if you start with the one on the right, okay? Now, remember, you have to remember, this is the classical Ben Franklin definition of current, okay? It is moving positive charges.
Yeah.
So, you wrap your thumb this way, boom, curl it, because you're assuming that it's a positive charge. So, when you do that, as that's, if you look at it from the end, okay, if you go like that, and you've got that charge going in and you wrap it around, so this is going to be going around like this, okay? So, because of that, this is going to experience a magnetic field that's coming down. The other wire is going to experience a magnetic field going like this. But then that current is going to be going this way. But, so again, your thumb is the positive charges. So that's going to be going this way, depending upon where you want to do this, where you're going to put this index finger. So, but that's going to be coming around like this, and then you're going to look at, okay, so if I'm going to do this, going this way, and that's going to be going like over here, that's going to be going down, that's going to tell you what's going to happen in terms of that force. The other thing that you can just do, if you don't want to go through all of that, this is the opposite of about everything that you've ever been taught. You've always been taught that likes do what?
Repel
Likes repel,
and opposites attract.
and this is the opposite.
Mm-hmm.
So in this case, likes attract, and opposites repel. Okay? So since these currents are going in opposite direction, and again, you can either go through the whole thing with the magnetic fields and the currents and do all of that, or you can just do this. So, you also, when you choose that answer in that multiple choice question, you have to look at how they're defining the system. So this is why you've got that X, Y, and Z axis off to the left. Because your answer has to be in terms of how that particular system is defined. Okay? Now, on number one, on the numeric value of the force per unit of length. So you're going to start with F equaling mu naught I1 I2 over 2 pi r. 2 pi r is just basically the circumference part of this. So what they want is the force per unit of, and there's an L on there. So the force per unit of length, all you have to do is find that force and basically move that L over. So if you divide over, that's how you're going to get your force per unit of length. Okay? Pretty simple. So that answer in number one should be something times 10 to the negative fifth. Okay? And then, to get your answer to number two, because that's newtons per meter, so the units on number one are newtons per meter, because it's force per unit of length.
Yep.
Then you just want to get rid of the meters, multiply that by your meters, boom, you get newtons. So both your answers to 1 and 2 should be something times 10 to the negative fifth. Okay? Now, judging by the spirited discussion, I'm guessing there might be some disagreement about the answer to number 3.
Yeah, we need help, Berg.
Okay?
We do not need help. It's B.
Woohoo!
Wow.
That was pretty okay.
I'm confident.
Okay. So why are you so take me through the thought process?
Oh no, that was earlier today.
Yeah, someone used ChatGPT.
I'm checked out, bro.
Yeah. he's
So
checked out.
basically, a little bit of this, a little bit of that.
He has his limit for
Yes,
his
currency, of course, is.
Hey, Shannon, let the teacher
Yes.
explain.
Just ask this.
No, he asked that.
2 more gallons of water.
Why are you like that? Why are you
Now,
I'm trying to listen.
what I did when I worked this problem is that I actually thought of it instead of a circle, I thought of it in terms of a square. Okay? Because that made it a little
The
bit
grass
easier
ain't-
for me
Okay,
to
wait,
visualize.
what?
Okay.
Same thought process.
What do you mean it's
Okay? So I
Why are we
thought of
changing
it
the limit?
as a rectangle like this. Okay? Because it just made it easier for me to see which direction the current was going.
Yeah.
You don't have to, that's just what I did. So on this one, the current is, and they tell you the direction of the current's going to go like this, which means it's going to be going this way, and this way. Right?
Yep.
Cool. Now, you want to know which direction the external magnetic field should be in order to produce a torque on the loop that is clockwise around the y-axis. Okay? So imagine this is the loop. Okay? The y-axis is like here. Right? Here's your y-axis. You want to create a clockwise torque. So remember, righty-tighty, clockwise. Come around like this. Okay? So I want this side to go down, and I want that side to go up. Okay? That's going to create that clockwise torque. But it's important that you understand which axis you're trying to make this thing spin around. So it says, hey, we want to around the y-axis. If then it said, hey, we want to spin around the z-axis, then it would have gone like this, which would be almost impossible to do. Or it could have gone around the x-axis, which would have gone like this. Okay? So you can make it go around like this. You can make it go around like this. You can make it go around like this. That's why they had to specify, hey, which direction is it going to spin around? Okay? Cool with this. Now, so start with this idea. You want this thing to be a torque that is clockwise around the y-axis. So I want this side to feel a downward force, and I want this side to feel an upward force. Okay? So I'm like this. I want this side to go down. I want that side to go. I can't have them both going down and both going up. One has to get pushed down, one has to get pushed up. Okay? So, let's say that I want to start on this side. Okay? I pick a side. I pick this side. I'm going to start with this side. So I've got the current going this way, right? Now, which direction, this is this wire. Which direction do I want my bottom fingers to point? Downward. So I've got current going this way. I got my bottom fingers pointing down. Which direction does my index finger point?
Negative X.
Inside.
On the left side, which would be the
Negative X.
negative X.
B.
To the west.
Famous Burkina, that's all.
Now, hold on. But let's say I started on this side. Okay? If I did that here, and now that I have established that I think I want the magnetic field to go in this direction, if I did this, the current would be going this way, the magnetic field would be going that
No
way.
force.
No force, because it's parallel.
So it won't move.
Yeah. But what about over here?
It looks like we're gonna be.
So, again, if you assume that it's going
Negative X.
from right to left, I want this side to get lifted up. Right? So I've got my current going this way, right? I think the magnetic field is going in that direction. So then my force fingers would get lifted up. So that's where that's consistent. So in both situations, I've got this side being lifted up, and I've got the other side getting pushed down. That's why it's going to spin in that direction. Does that make sense? Everybody cool?
Because if you do it right.
Oh. Now, on number 4, I want to make sure everybody understands number 4, because there's a lot to unpackage on question number 4, even though it looks like a simple multiple choice question. So you've got, this is what we talked about yesterday with that conducting plate. And, okay. So here's your positive side of the terminal. And this has dots. So the dots mean what? Magnetic field is coming out. So it would be like this. So if you were to physically set this up, you would have a wire like this, and then you'd have like a copper plate or something in here. But then I'd have to have a magnet near it, creating the magnetic field. So I'd have a wire with a current moving in it, and then I'd have a magnetic field created by a magnet that's beside it. Okay? So it's handy if you have that visual. So I've got to have two things. I've got to have a current, and I got to have a magnet. So start with this idea. If, and this is a huge if Ben Franklin is right, and there are positive charges going in this direction, okay? If they're positive charges, horizontally, if they're positive charges that are coming across like this, horizontally, which is the positive and which is the negative side of the plate? Horizontally.
Positive left, negative right.
You're saying positive left? Okay, so you're saying positive left and negative right.
Yes, that's right.
Okay? Why?
Because two forces would push each other.
Yeah, so it's going to be repulsed by the positive. So horizontally, what is the direction of the electric field?
To the right.
To the right, because a positive charge is going to feel pushed in this direction. So horizontally, the electric field is pointing to the right. So that's the first electric field that you've got, is pointing this way. Now, if it is positive charges, right-hand rule, positive charges going this way. What am I going to do with my index finger? In or out? Out. Fingers are going to point down. So what's going to happen is that I would create positive charges that would drift downward. Okay? Positive charges would drift down. That would leave negative charges up towards the top. Okay? So vertically, what's the direction of the electric field? Vertically, the electric field is going to point up. So that's something that we could measure. We could measure the voltage. Okay? We could hook it up and go, hey, where's the voltage? Okay? That's something we could easily verify. So if it's positive charges, you would see one electric field pointing to the right, and you see the other electric field pointing up. If positive charges were actually moving. Now, if it's negative charges, what's going to happen? What's the direction of the electric field? Is the horizontal electric field still pointing in the same direction?
Yes.
Alyssa.
Why would the electric field point up?
Because if it's positive charges are going to feel a force that would push them down. So you would have positive charges down here and negative charges up there. Okay? So if I release a positive charge towards the bottom, it would be repulsed by the positive charges at the bottom, and it would be attracted to the negative charges at the top.
So if you added in like another positive charge?
Yes, so that all that's doing is just defining the electric field.
That's what he
Okay.
explained. So the force
So
is gonna
if
push
it's
the
an
proton.
electron, an electron was here. An electron would go still in that direction. An electron would feel repulsed here, and it would be attracted there. So horizontally, whether it's a positive or a negative charge, the horizontal electric field remains in the same direction. Okay? That doesn't change. But now, if you use the left-hand rule, so I've got a negative charge that's coming like this, right? I got a magnetic field that's pointing out. My fingers are going to point down. So if it's negatively charged particles within that plate, within that conducting plate, I would push negative charges to the bottom, and I would push positive charges to the top. So if that's the case, vertically, what's the direction of the electric field? Downward. Because a positive test charge would go in that direction. So this is how you settle the debate. Was Ben Franklin right? Positive charges? Or is it actually the negative charges that are moving? So, with all of that said, what do you have as your answer on number 4? As well you should.
How did they know that? They
Wait,
tested it.
Wait, very careful.
Like, how did they test it?
E.
All you have to do is just measure the voltage.
Like measure your brain.
So then you can use
See that the charge is
voltage equals E. So if you can measure the voltage across the plate, and you know the distance, how far apart the edges of the plate are, you can measure the electric field.
That's how they figured out it's an electron.
You just said it went up.
No, for the proton it goes up, but for this it goes down.
So we're doing electron.
It's an electron, so it goes down.
It's
always
Literally the other day he told us it's always a proton.
Oh.
No, we didn't.
That was the last part of the West one.
No, he means like,
Like he explained
you're gonna
it.
assume it's always a proton in the direction of a current.
But with this one, you're actually going off of the true reality.
Berg, is this
So we're
question on the
thinking about
test?
when and over.
The concept is absolutely promised.
Bro, I'm gonna get an ab, bro.
Dude, I'm so gonna proton.
No, Jack, I'm not.
Okay, so let's talk about number 5. Okay? So on number 5,
Huh? And
this
there's
is a
my
good
A.
question.
Number 5 is pretty, we're slightly
Okay? So you got 2 wires. The top one has a current going in this direction. The bottom one has a current going in this direction. And you want to figure out the net magnetic field due to these 2 wires at point P, right there. Okay? So you got to do the right-hand rule twice.
Yes.
So based upon the top wire, what's that dot going to feel? X's or dots? That's going to feel X's. So from the top wire, I'll call it XT. Okay? Right? So you got from the top wire,
Yep.
that's going to feel X's. Now, on the bottom wire,
Wait, circles on top, right?
I curl it this way. So from the bottom wire, you're going to feel O. We'll put that OB. O's from the bottom. So right away, these are in opposite directions, right? Right? Now, are they exactly going to cancel out? No. Why?
Distance, not distance.
Because what's the only way they can cancel out?
Not the same.
Is if you were right in the middle and both currents were the same.
Why are the circles right next to X? Shouldn't they be down a little bit?
It's just, it doesn't matter. I mean, yeah, they're
It's
all
based
on
off the
same-
bottom and the top. They're two separate
All I'm saying is that at this point, at this distance, okay, that's what you're focusing on. I'm gonna have dots coming out, and I'm gonna have X's going in. Yep. Now, don't get hung up on where I drew
In
them,
the camera.
okay? Not
Yeah.
the point of the story. The whole point of the story is that they are not going in the same direction. Okay? Now, which one is going to create, at this point, which one's going to create the stronger magnetic field? The top wire or the bottom wire?
Top one.
Sydney, what? Why? It's closer. So whatever the magnetic field is from the top wire, so the magnetic field from the top has to be greater than the bottom magnetic field because it's closer. What?
Wait, so Bert, at that point you could make it equal if if you change the currents though, right?
Oh, you could.
Okay.
But I'm just saying, since these are the same currents.
At that point, they can't do it.
Yeah.
It's a future question.
So, the whole key to this is that you look at how you determine that magnetic field. Because it's a wire and not a loop, you know, your magnetic field is mu naught I times 2 pi r. So, what I would do is that I would let, for that top wire, what are you going to let R be? Which sounds weird.
We're gonna let RB
Oh, the top one.
for the top one, 1/4.
Deal before. Okay? So from the bottom wire, mu naught I, 2 pi, what's that distance going to be? 3/4. So, are you going to add them or subtract them?
Subtract.
Because they're going in
Opposite
opposite
That's where I
direction.
went wrong, Berg. I added them.
I would make this positive, and I would subtract that one. So there you go. The answer, obviously, on number 5 is not C.
That would not make sense.
I almost could say.
Wait, what is that?
It's Jones barbecue and put beside it.
I actually told him once.
All right. Any other questions on it? Going once, going twice.
Wait.
So,
Berg, after school, I'll ask you
Grab
questions.
Wait, here you go.
Oh, never mind.
I was yes and no on this.
Bad.
What is the
Yeah.
tomorrow,
No.